And we move to the next presentation from Felix Jacquel from University of Wisconsin, and he's going to talk about precision characterization of thermal circuits and noise of TES microcalorimeters.
Good morning, everyone. So this presentation was supposed to be given by Avirup. He wasn't able to be here this morning, so I apologize that you'll have to put up with me for a little bit. This work was done at Wisconsin, but it's based on devices made at Goddard and also at NIST. Just a disclaimer here, this is really not about any performance characteristics of any particular device. This is more about the technique, sort of a workshop talk. So our motivation is that we'd like to study hot gas in the universe. This is an important problem in many astrophysical questions. Where are the missing baryons, the missing metals? How does the metal transport in the galaxy work? So we're dealing with relatively diffuse sources. Million-degree gas, emits, and these very densely spaced lines at relatively low energies. And we'd really like to sort out these lines, and to do that, you have to have a detector that has a resolution certainly better than about 2 eV. Can we actually make such a thing? Can we make it with the pretty large size that we would need for a sounding rocket mission? That is an open question. We think there's a path. So here's kind of a diagram of energy resolution that you might predict given some sensitivity alpha and giving some beta and some excess noise. There's some data points here that have actually been demonstrated, and it seems there is maybe a realistic path to extrapolating somewhere out to here where we would like to be. Well, you really need to understand, though, what kind of numbers can you achieve here and how do you measure these. So here's a crazy flow chart, sort of right off the whiteboard. I'm not asking you to follow through with this and understand this, but there's these different techniques that you can bring to bear on characterizing your devices. And it's quite important that you realize all these connections and try to cross-check your measurements, because there's plenty of ways this can go wrong. Just so you know, most of the data I'm showing here is from this device. It's a very high performance device. We're very happy with it. I'm not going to say much more about it. So back at ASC 2016, Jack Sadler suggested, hey, you know, your device is probably a weak link at some point in the transition at least. And he realized that you can make terribly good use of that to calibrate your shunt resistor. So what you do is you put an AC excitation on it, and you get these little steps at certain voltages that are related very simply by a constant to your excitation frequency. And you get the current steps, and you know where they're supposed to be, so you can get a good measurement of your shunt resistor. We do that. You can do that by either adding this to the bias. We find it more productive. It works better for us if we add it to the coil, to the field coil that we have around the device. So we've done this a number of times now. I'm just showing you some examples here. These are different shunt resistors, so different devices here. So for this shunt resistor, you get the same number. You can do this versus frequency. You can do this with moly copper devices, which are not really thought to be weak link devices so much. Or you can do this with something that has niobium leads. Works beautifully. You can make other fun plots. I'm not going to talk about these right now. You can ask me later if you want. This is a pretty standard thing that you also need to do. Everything scales with the shunt resistance. And this is an important input parameter for all your other models and calculations. Just wanted to point out that you really should do this when you report this. You should do this versus basically the point in the transition where you are and kind of see what your systematics are. So here's the G that you get as you go higher and higher in the transition. You can see, you know, this is a pretty expanded scale, so it doesn't really vary too much, but you have to check. All right, this is another pretty standard thing. I'm not going to belabor this, but Mark Lindemann suggested that, you know, you need to take care of your stray impedances when you're doing complex impedance measurements, and you will realize that basically you have the superconducting and normal transfer functions. You can find the ratio of these. The shunt resistance you already know. Your device resistance you already have measured from IV curves. So at that point there's really only one free fit parameter, and you can do that fit. It comes out beautifully, and that's something you should always check. Okay, so let's move on to what you actually get. So you measure your complex impedance. You get your beta right away by going to the high frequency limit where the device thermal system can't keep up with the current variations anymore. And then you get your alpha sort of from the low end, and you know where this roll off here is, or the peak in the middle. That's your dominating time constant. So this particular device, you know, it looks like almost a perfect semicircle, but if you look closely, there's a pretty systematic residual here. So what do you do about it? Well, the usual thing. This was a simple one-body model. You go to the two-body model. Here's just quick the fit results from this previous one. There's nothing too remarkable here, I think. The G is something you put in that's already measured. You get heat capacity out. It varies within a few percent if you don't fix it from some other measurement that you do. Alpha, beta, the lower you are in the transition, the higher they usually are. Okay, two-body model. Of course, it's going to look a little bit better. So now you've really kind of taken care of most of these systematics. This is starting to look pretty flat here. So you say, okay, I'm probably done now. But do you really know? No, you don't know. So what else can you do? Okay, so here's the fit results. So here it looks like we have about a 10% heat capacity in that hanging body, probably the absorber. All right, so you really set out to maybe understand the noise. So what does that look like? Well, here's the measured noise spectra, and here's what you would get from the single body model. And down here where the thermal fluctuation noise dominates, it looks like you're doing fine. And out here, well, it looks pretty wild. All right, so two-body model. Okay, now you're doing a little bit better here. So you've got this extra hump here taken care of, right? That's the extra thermal fluctuation noise between your absorber and the TES. And out here, it still looks pretty wild. All right, well, that's nothing new to you. There's this excess noise term. It's always parameterized as such. And you can look and see if that actually works out. So you form the ratio between this excess noise and what you predict for your Johnson noise, and you can plot that versus frequency and check if your assumption is actually right. Looks pretty flat here, so probably this is good. You know, out here it's of course just noise of the noise if you want. Well, so then you can plot your M or M square versus the point on the transition where you are. It has some systematics here. I'm not sure if anybody else has seen this or not. I'd be curious to know. And so then here's your final product. So this is not a fit. This is predicting the noise from the transfer function. And you know, the only free parameter after that is the M. Okay, what more can you do? Well, you can look at pulse shape. We tend to do this with our laser source. These detectors have high enough resolution that you can resolve all these peaks. That's nice because then you know that you are in the small signal limit. and you also know what the absolute energy of your pulse is. Okay, so what does that look like? Well, here's again the one-body model, and I apologize, you can't see terribly much. Here's the residuals, and these are about a factor of 10 higher than they are here on the two-body model. And the two-body model is not such a terrible fit. I think we could still work on that a little bit more and make that better. So perhaps at this point then you've kind of done enough to convince yourself that you're right. All right, so one more neat little thing you can do. It doesn't really give you anything new. It's just kind of a trick if you have a large surface, a large transition surface that you'd like to map out, and this is also something that was originally suggested by Mark Lindemann. Well, usually you do the serial thing where you sweep your excitation to measure the complex impedance. He said, well, you can also just put in a few sine waves simultaneously and measure the response. And he did that with 3 physical lock-ins back then. And of course, that's tedious, and maybe that's why it hasn't really caught on. You can just as well do this in software, of course. So we do this live. You don't have to do it live. And you can have, you can choose your frequencies, and you can distribute them where you think you get interesting information. And you pack all your power into those points. And, then you can run. You can, for example, sweep through the bias. And one thing you should check is that your AC excitation isn't too high, that you deviate from the, shown in blue, the DC IV curve. Okay, what does that get you? Here's an example of a relatively weak link dominated device that has these relatively complex structures here in the critical current. Down here, the axis is always the coil voltage, so what you put on your magnetic field compensation coil. And so you can make these pretty maps of alpha and beta, and well, these are not so interesting here. And you can then see, what might be the optimum operating point for your device. Okay. With that, here's my conclusions. Thank you.
Thank you. Is there any question?
That's very nice work, Felix. That's excellent. So you can predict the pulse shapes from the measured parameters, which is awesome. That's the best I've ever seen. I'm really excited to know how accurately can you predict the gain curve, meaning the pulse height that you get from the optimal filter from the predictions of the pulse shape?
That is a wonderful question. Unfortunately, the answer is we haven't done that part yet. So I think the data is right here, and just that one step is missing in our analysis currently.
Other questions?
It's quite a nice work and a nice talk. Could you back to the alpha and the beta?
Yes, yeah.
No, the bias point stuff. The one single body and the two body.
Yes,
yeah, that one. So it's this a two body. Now beta is about reach to above 7 or how about 5. Could you go for one body model? Previous another one, yeah. So the it looks like the beta has changed some reasonable way. Is there any good explanation? I thought that two-body model should have a less impact, in particular if I look frequency, the spectrum.
Yeah, you're right. The beta should definitely be the same.
Yeah. Somehow a bit different. Do you have any comment on that?
I don't. It's possible that these two slides perhaps were done at different base temperatures. We usually do this versus base temperature.
Okay, another?
Thanks. A quick question about the coil voltages. What range of magnetic fields roughly correspond to the voltages that you showed on slide 20? So you're looking at
at the field dependence I showed here. So this is, it's roughly a microtesla from end to end. For the AC excitation, I can't tell you because, of course, there's a roll-off, so I don't know what the absolute field magnitude is.
Okay, so thank you again.